So, how's it going, people? Happy Friday. I know that at least a few people have been continuing to struggle with getting a COGS 118B environment built. I found this slide from Spring, which was like the most common ways in which stuff goes terribly wrong, right? So if you still haven't managed to get a fully functional environment on your own laptop, I just wanted to reiterate to you, and I'm sorry I didn't have this a week ago for you, but essentially there's some stuff in the environment which is not pip installable. It's got to be installed by you separately, right? And if you don't build these things first, like the LaTeX or the Pandoc, then it can definitely cause some issues. So probably most of you have already figured this out, or you've given up and you're just using Data Hub, which is always an option. But if you still haven't got your own personal Conda environment, this one's helpful. As you're doing things like assignments, hi, could you please quiet down? Thanks. So as you're doing things like assignments, I do want to remind you that stuff can go terribly wrong, okay? There is this way in which it can look great for you in your notebook. The math is beautiful. It seems like it rendered what you wanted, and then you're going to lose points when you turn it in. Why does this happen? Because the process of turning into Gradescope generates PDF from the notebook and throws the PDF over for us for manual grading on the math stuff. That process of generating PDF uses a different LaTeX engine than the one that renders on your screen in Jupyter Notebooks. So you can absolutely use some garbage LaTeX, which is not good LaTeX, that Jupyter Notebook's rendering engine goes, I know what you mean, I will autocorrect that for you. And it looks like it renders great. But at the moment of assignment generation, when it runs it through regular old LaTeX, well, that's where you get those errors that you don't even know about. So how can you prevent those errors you don't even know about? The main thing I want to suggest to you is if you use file export to PDF via LaTeX on your own Jupyter Notebook right in front of you, you've got an approximation of what it's going to look like when it actually generates. And if you did the Conda environment right, and you have the exact same setup that we do on Gradescope with a MikTeX installation and a Pandoc installation and all that stuff, then this is going to be exactly what generates. So you can generate PDF for yourself and see what went wrong if you used bad LaTeX commands. Does anybody have any questions on this? Yeah.
So I usually use like the Conda Navigator for just managing stuff because I'm lazy. And it's really slow on my computer, so usually initializing the environment and stuff takes like a long time. If we didn't have this stuff installed before, is it imperative that we have to remake the Conda environment, or is it?
I don't know if it's imperative. What I know is that people are having troubles. And my first advice that seems to solve many of the troubles is if you have an installation where you put in LaTeX first, then you put in Pandoc, and then you do the Conda environment build after that. So at least that's solved several cases that I've helped work on. Okay. So generic advice also exists on this slide on how to have not bad LaTeX. But again, my main thing is export to PDF via LaTeX on your own computer so you can see what it will look like. Woof. Any other questions? Procedural, logistical? Yeah.
On the first assignment, the opening part says here's some resources for LaTeX, and they're just not there. It says Scott, insert here, please.
Oh, good. Okay. Well, when I said Scott, insert here, please, I didn't reach Scott, apparently. We have a resources repo. I will make sure that we put those links, some of which I think he put in the practice assignment, actually. Wasn't there some links in the practice assignment?
I don't know if it was LaTeX related, but I can go check.
Okay. I feel like we tried to do this at least twice, and one of them maybe failed. So I will also, because A1 is a repo, I can update the repo, and you can pull the changes. And theoretically, it should all work great. So we can do that too. OK, so thank you for that. Any other logistics kind of issues? OK, I got some really good news. This is the final day that we're going to be doing math preamble. Starting next week, we're going to work on clustering, which at least you will recognize as a machine learning task, right? So, so today is kind of a hodgepodge. I want to do a few things. I want to finish up the idea of doing Bayesian estimation with Gaussians, which we were basically 3/4 of the way through anyway. But then I want to talk about generic issues that arise in machine learning. If you were in my 118A class, you've heard me go on about this at least a little bit. But fundamentally, everything in machine learning is linear algebra. And if you don't treat your data right, then you're going to get yourself messed up. Okay? So we're going to talk a lot about the nature of representing data as vectors and matrices, and how some things work and don't work in metric spaces. Okay? So that's what we're after today. But let's just finish up the normal distribution, because you all have seen the univariate case, right? Well, if you got one variable like height, this is easy. Everybody's familiar with this. Okay? We talked about these elements of it too. So with the univariate case, how can we do Bayesian estimation? Well, unlike with the coin flipping example, I am not going to derive this for you, because it's like a page and a half of math, and you've already got the idea. Bayesian estimation for at least a few cases, like Bernoulli things and Gaussians, well, there's an exact answer, right? You can do the math derivation, but this isn't a stats class, really. I just wanted you to have the experience of it, okay? So you can do the derivation. You can find out what is this reduced form of updating a Gaussian prior with a Gaussian observation and getting a Gaussian posterior. Gaussians are great because prior, observed likelihood, and posterior, Gaussian is its own conjugate prior, right? So it's its own conjugate. It's a weird little thing. So what does this even mean? What we're trying to do is we're trying to estimate the mean of something. And this is Bayesian estimation. So we have a distribution of potential means. When I update a standard deviation here, I am not updating the standard deviation of the distribution. I'm updating the standard deviation of our belief of the mean. We're trying to estimate the mean. We have a distribution of potential values for that mean. And on the posterior, we have a new distribution of the mean of the thing we're trying to estimate. Okay? I want to make that important, clear distinction. The standard deviation is not the standard deviation of the data set. It's the standard deviation of our mean estimates, okay? So there's another set of math where you can do the same thing to estimate the standard deviation rather than the mean, okay? And get the distribution of standard deviations and update that. So one thing I want you to note about the final form of this answer, as we're updating the posterior mean, what we get is a mixture. A and B, those are terms which are related to the standard deviation on the prior and the observed standard deviation, okay? So essentially, this is a mixture. It's like my observed data here, my prior here. A and B are mixture terms where we're going to make a posterior, which is a linear mix of the prior and our observations. And the reason that works is because this damn thing's an exponential, right? And the things that were inside the exponential become linear outside it. So that's the deal, right? And you can update your system and on successive estimates converge closer and closer to a good idea over time, right? This is the usual Bayesian update. Okay, so I know that the form of the equations is a little bit new, but hopefully the idea is clear. But let's take that moment. What is confusing here? What are your questions? Yeah?
Sorry, I forgot. What does the phi function mean?
The phi, oh, sorry, you mean theta? You mean this thing here?
No,
This.
at the chart at the bottom, underneath likelihood. It says phi x given theta.
Oh, that's the likelihood function, right? So that's an observed data. Sorry, I catch this from a set of notes where the notation is slightly different. So this is the likelihood function, the data given the parameter. Okay, so in their notation, phi it's just another word for function, right? Phi is f in Greek, I think. Any Greek people in here? No? Okay, so nobody has to stand in, but my bad Greek, I think phi is the f in Greek, so it's just another function, right? They're just trying not to confuse you to not make it the posterior or the prior. But it's the likelihood function. It's the likelihood of the data given the parameters. Yeah?
What are the C1, C2, C3?
Constants we don't give a flying you-know-what about, right? Because when we do updates, we always do this, remember, proportional to. And because we do it proportional to, we don't have to care about any constants. We can throw them away to make our lives easier. Last call for questions? Okay, so let's show an example, right? We have an assumed prior on the normal distribution. So this normal notation, just a reminder, that means the mean is 4 and the standard deviation is 8. That's our assumed distribution of means that would represent where we think the true mean actually lies. Now, they're doing something really extreme here just to show you a simple math working, which is to pull a single data point, okay? And the crazy thing about Bayesian update is that if we repeatedly draw single data points, well, we can converge to a decent estimate after a bunch of single data points, okay? Try doing that with maximum likelihood estimation, okay? So we draw a single data point, And then, well, again, we don't have to care about all these stupid constants, all right? You could go ahead and run the equations where we take, here is my prior, right? This is the form of the exponential of the Gaussian, my parameter theta minus 4, which is our assumed mean, right? And here is our single data point, which is is 3 minus the assumed parameter. And you can collapse that and do the math and get down to this form that is actually just what was on the last page, okay? Like, it turns out that we just have this linear mix, which is based on the standard deviations observed, and we end up moving from a 4,8 to something that is, God, 44 over 12 would be like, what is the final thing? My brain is broken. 12, 24, 48. So this is a little bit more. Is it a little bit bigger than 8? Who's better at this kind of math than me? 44 over 13? Somebody got their calculator out, so I don't have to. I think it's a little bit bigger than 8, but I might be wrong. Okay. Yeah.
I think it's smaller.
Oh, it's a little smaller than 8?
Wait, what's that say?
44 over 13.
Yeah, I think that's like closer to miles.
Okay. All right, so a little smaller than 8, right? So we updated with a single data point. Okay? So again, like I said, you can use the formulas on the previous page to check that you get exactly the same thing, right? You don't have to do the full derivation and calculate it in the exponentials. You can just use this linear update equation to just calculate, oh, look, if I'd bothered to go to the next one, it says it right there, 3.38. Thanks. Right? Okay, so with that fresh in your head, I want to take a break for a second. I hope you've all got a computer in front of you that maybe has the ability to pull the lecture repo, because there is this thing, this notebook in there. And if you could load up this notebook, okay, I want to take this moment to cement this idea of successive updates for you. I'm going to give you 5-6 minutes to do this little task, because what you'll see is that I've defined this normal update function, which just encodes that linear mix, okay? And I've given you a little dumb problem, right? And the idea here is that we're trying to estimate the age of students in a particular class, okay? And we have a prior estimate of the age of students from last quarter. There is some true process that's generating the age of students in this class. Most students in this class might be, say they're seniors, right? But some of them are a little bit older seniors, some are a little bit younger, there's some juniors mixed in, there's like 5 grad students. So every quarter, the age distribution is going to be a little different. And every quarter, we're going to draw a sample from this real process. So over time, over 6 quarters, our estimate should converge towards the real value. And by doing it as a Bayesian update and not waiting for the end of 6 quarters and just calculating an empirical mean, what we get Oh, that's good. What we get is we get a refined estimate earlier in the process. We don't have to wait for the end of 6 quarters. And this kind of online update of an estimate is something that is super common, okay? Like engineering. Anybody take electrical engineering kind of classes in here? Raise your hands. Anybody done filters? Yeah, like filters like Kalman filters or anything like that. It's this process. I wish I had a filter right now. Okay, so here's your task. You can see one go of taking the prior, generating an observation in this quarter, and seeing what the post is and comparing it to the real. I want you to take the code above, put it in a loop, and move your prior through the observations to get a post, and then take that post and make it a prior. Draw a new set of random variates for the new class, and do this several times and watch how the posterior estimate changes over each one of these next 5 iterations, okay? So I think you've all got enough Python that you can make a for loop and do this 5 times, right? You just need to take your posterior from the last time, turn it into your prior of the next time, and redraw a new sample. And print out the posterior on every element of the loop. So do that now. Give you like 5 minutes. Obviously, don't forget to do the update function call after you draw the sample. Otherwise, this won't work. So if you did something like this, this is kind of what I was after. To loop over 5 times, take the previous posterior, which had already been defined in the cells above this, and make it your prior. Draw a new sample, calculate a new posterior, and print that posterior. Now, everybody's going to get a slightly different answer here because I didn't do what? Yeah. I did not set a random seed, right? This is a bit of machine learning black art that you need to know. So many things in machine learning involve random numbers, right? Random number generators may or may not be something you understand, but let me tell you a vague idea how they work. They start with a seed number. See, random number generators aren't actually random, okay? They're not really dice rolling. They are deterministic algorithms. But what if you start them at a seed like 42, then the next random number they generate is deterministic. It starts from that number 42, and it goes through a sequence. And the sequence is random, but repeatable, because if I restarted it at 42, I would get the same sequence. Okay? And if I started at 43, the sequence of numbers is not even vaguely close to starting it at 42. That's a key element of how random number generators work. So, if you want repeatable results in machine learning, you need to know the random seed you start with. And a lot of people will say, here's my results, I publish it online, and here's the seed that generated those results, so you could replicate down to the 25th decimal place the results. Okay, you were raising your hand again?
Oh, you answered.
Okay, yeah. So you can set seeds, right? You can set the seed in random number generators, but I'm not doing it here. I encourage you to figure out, whatever system you're using, how to do that. Okay? So at any rate, your results might look something similar to mine, or they might be totally different due to chance. But in my case, running it just now, I converged towards the right estimate of mean, but then I went too far, right? The right estimate for mean is like something like 21.7, if I remember right. Yeah, the real mean is 21.7. Okay? Now, noticing my results here, which is the first time I looked at them, because I just blew this notebook together in the last half hour before class, I have a funny feeling I screwed something up. Do you see how the standard deviation does not converge to 2.8? But it's not far off 2.8 squared. I got the feeling that the scale parameter in NumPy stats is probably variance and not standard deviation. And I passed it in as standard deviation. So, right? Classic blunder. All right, so that's the way iterative estimation works. It's not that hard. But the thing is that generically, if you're actually doing Bayesian statistics, you're probably working with something that is not so neat, right? You're not generically working with, I know the exact distribution, and the distribution happens to be something that I can analytically solve and do this simply. So if you choose to take a class beyond this one, which does lots of Bayesian stats, what you're actually going to be working with is universal inference engines. These are big, complicated pieces of software. Do you know what they do? Remember this process right here? They do this process right here millions of times and average over it. Okay? They're Markov chain Monte Carlo algorithms where it just like does Monte Carlo simulation, rolls the dice over and over and over again, and builds empirical distributions. Because that way you don't have to know so many details about the actual model, but you can just solve for any kind of distribution. Anyway, that stuff's above my pay grade. I'm not real good with that. But if you're interested, these are software packages like PyMC3 and PyStan. They're Markov chain Monte Carlo universal inference engines for Bayesian statistics. Feel free, knock yourself out. I'm not going to go there. All right, what I do want to do is talk about multivariate cases, because not just are multivariate Gaussians their own deal. Generically, when you do machine learning, you're not doing it on one variable, are you? Otherwise, you wouldn't be doing machine learning. Generically, you're going to be thinking about cases which have dozens, hundreds, thousands of variables. Okay? So what would it be like to take a Gaussian and move it from the bell-shaped curve you know into 2 dimensions? Well, that's not hard. Just take that bell-shaped curve and rotate it and make an actual frickin' 3D bell, right? It may be harder for you to imagine that in 4 dimensions. If it's not harder for you, please go to the math department. Okay? After a while of thinking about it, most people can kind of get an idea of 4 dimensions in their head. But nobody can do n dimensions, right? Generically, that stuff doesn't really work in my head. But in math, it does. And it's all the same math. All we've got to do is this. We replace the x that was a single x with a column vector. And each one of the rows in the column vector is one of our variables. Our mu, our mean, is now the same size as x. So if it's an n-dimensional data set, we have n means in a column vector. Well, if we have n means, we got to have at least n standard deviations. Well, it gets worse than that, people, because it's an n by n matrix that we call the covariance matrix. This sigma, this is the covariance matrix. And that covariance matrix, on its diagonal, it's the variance for each one of those variables separately, right? So every mean has its own standard deviation. But on the off diagonals, what we have is the correlation of variables with each other. Okay, so some things to note here if you're not real into linear algebra. Anybody know what this little t up here is? Who can tell me? Transpose. Why do, remember how the generic one-dimensional version of this is? It's x minus the mean squared, right? In linear algebra land, it's x minus the mean transpose. Ignore the covariance matrix, but you see right after the covariance matrix, it's x minus the mean again. So that's your squared term, x minus the mean, right? That's x minus the mean squared. But in linear algebra land, to keep things the right number of rows and columns, we need to have transpose on one of them and the regular version on the other. In linear algebra land, the first term in the multiplication determines the number of rows. The last term in the multiplication determines the number of columns. Right? So we take what had been a column vector and turn it into a row vector, so it's got one row. So our answer is going to have one row. The end is column vectors. So it's going to have one row and one column. That is, we're getting a single scalar number out of this baby. Okay? And that's good because the number coming out of this baby is the density function, right? We don't want a matrix coming out of this. We want for every given place in the space, we need one and only one probability. Okay, the rest of it is the normalization stuff that you're used to. Okay, let's look at what this means in 2 dimensions, which is about as high as anybody in here wants to go without more coffee, right? So if we have, again, this covariance matrix, which on the diagonals is, for 2D, we have x and y, right? So this is the variance in x and the variance in y. And this part is the correlation. That's what that row is, the correlation between x and y. So shape-wise, what do we have? If we have no correlation between x and y, and both of them have unit variance, this is our quote-unquote spherical Gaussian. Anybody ever heard somebody use that word, spherical Gaussian? So a spherical Gaussian is the bell, right? So it's the standard deviation tells you the spread, right? Twist it into a second dimension. Imagine an actual shape of an actual bell. It's the same spread no matter which way you slice it, right? When you look at it from the top, it looks like a circle. If you think about this in additional dimensions, it becomes a sphere, right? In 3 dimensions. And in 4 dimensions, it becomes a hypersphere. Okay? Yeah?
Should rho sigma x, sigma y the covariance of x and y instead of correlation?
So the rho is the correlation,
Yeah,
and the
rho is-
covariance is correlation times sigma x, sigma y.
Gotcha.
Yeah. So I may not have said that in the best way. Rho is correlation between the 2 variables. And rho sigma x, sigma y is covariance between the 2 variables. Thank you for clarifying that. I could easily have said that wrong earlier. Okay. So generically speaking, I want to point out a few special cases here, right? There's something called axis-aligned Gaussians. These are Gaussians where there's no correlation between the variables, right? So, oops, I got my thing out of whack here, but so the entire top row is rho equals 0, no correlation, okay? Sorry, I should have put a red thing around this one too, but I didn't, right? The 2 outside ones, they are spherical Gaussians, but in one case, the standard deviation is smaller than in the other case, right? But here, this middle one, it's axis aligned. There's no covariance because the correlation between the variables is 0. So the covariance is also 0. But it's not spherical. One of the 2 variables is more spread out than the other. Okay? So, why am I talking about spherical Gaussians? There are clustering algorithms, naive Bayes, which assume spherical structure in the data. There are clustering algorithms that do not. Okay? So it's important to understand what you're assuming. The one thing about all the axis aligned is that x and y are independent of each other, right? If there's no correlation, you might as well be rolling separate dice for x and y, right? But if there is correlation, then the value of x tells you something about the value of y. Okay? And so all these other cases, well, they have different levels of correlation between the two variables. Okay? So try to make sure that this all makes sense to you, because you're going to see this kind of thing not just here, but repeatedly. Okay, now let's talk about the fun stuff. So, again, not just here, everywhere we're going to have this generic n-dimensional problem. If you're trying to understand something happening in n dimensions, you need a lot of data samples. Why? This is something called the curse of dimensionality, also called Bellman's curse after a famous mathematician. So, the curse of dimensionality is because when you're in high-dimensional space, shit gets wacky fast. Not only is it impossible to imagine 5-dimensional space, when you get to 100-dimensional space, your ideas of space are ripped apart. Your intuitions that work here well in 3 space do not hold in 1,000-dimensional space. Okay, we're going to talk about that in a second. But one of the best ways you can see that is this stupid little set of graphs. There are 100 data points, uniform random distribution in this one-dimensional case. There are 100 data points in uniform random distribution in this 2-dimensional case. And in this 3-dimensional case, and in this 4-dimensional case that you can't see all 4 dimensions in, but we have a 3-dimensional slice out of a 4-dimensional hypercube. Okay. So, when you look at, this is the classic mathematical version of this, take half of each axis. How many data points are inside half that axis? This is like, what if I sampled, right? What if I have this one-dimensional space and I grab a sample out of it? Do I get an accurate representation of the whole thing? So if I grab half the space, in the 1D case, in this particular roll of the dice, I've got 42% of the data. And obviously 50% of the data would be the average value, right, over many such draws. Okay, and in the 2D case, half of each axis, well, now I've only got 14% of the data. And when I go to 3D, it's down to 7%. The progression is to the power of D, okay? To get accurate sampling, we need to grab samples to the power D in D dimensions. That's an exponential increase with number of dimensions to get a good sampling of the data and to accurately represent the distribution. You can also build this in your mind with like dividing up the data space into cubes and seeing how that works. One of my favorite versions of this, the one that's just kind of mind-blowing, is the sphere inside a cube. Okay? In 2D, you can draw a sphere inside a cube, inside a square, right? A circle inside a square. And in 3D, you can draw a sphere inside a cube. And your normal space intuitions say, yes, the sphere is smaller, but not by a lot, right? What's missing is, well, the corners, right? Wherever the corners are. These corners are missing. So the volume of, or the area of the circle inside the square is most of the area of the thing, but not all of it. And inside a cube, well, now you've not got 4 corners, you've got 8 corners that are missing, right? In the limit as d goes to infinity, the ratio of volume of sphere to the cube goes to 0. Eventually, the sphere has 0% of the area of the cube. Boom. Right? So, whatever, right? You don't have to follow this exact math, just the idea that high dimensionality is super hard to sample. And when you're calculating statistics in high dimensionality, shit gets wacky. Okay? So, how can we deal with this? Well, generically speaking, the first statistic you're going to have a problem with as you go to high dimensionality are the quote-unquote higher order statistics, variability statistics, covariance matrix. Covariance matrix, if you're trying to, like, you've got, oh, I've got some data, I'll calculate the empirical covariance matrix. Well, if this is, say, genomic data with 23,000 variables, right? 23,000 variables, say 1,000 samples, because that's about as many samples as you're going to get in biological data, right? 1,000 samples, 23,000 variables, you already know you're in trouble. Calculating a covariance matrix at that level, you just might as well not. Because you know that random data, randomness in the die roll, is going to be seen as God's honest truth. And randomness in the dice roll at 23,000 dimensions is really random. Okay? You may have one data point in half of each axis with 1,000 data points going in. Okay, so how can we deal with this? One classic statistician's way is the so-called shrinkage operators. It's pretty easy to understand what a shrinkage operator is. Once again, it's a linear mix of what you observe, right? So this measurement I'm making, the maximum likelihood estimate, that is, if this is the covariance matrix, this is take the data, calculate the covariance on the data, okay? Okay, so I take a mix of the empirical maximum likelihood estimate and some model, right? What's the model? Usually it's the identity matrix, 1, 1, 1, 1, 1, 1. A spherical Gaussian, right? Because something that's ones on the diagonal for the covariance and zeros everywhere else, that's a spherical Gaussian. So my dumb, uninformative prior, a spherical Gaussian, mixed with my actually available data. Alpha is a little parameter, a hyperparameter, that I have some method to set. I'm not going to talk in general what that is, but there's some method for setting that. And I mix the thing I observed with this dumb, uninformative prior. Okay, so you should definitely take a look at scikit-learn's docs, because they implement this right here with shrunk covariance. All right, so one other thing before you run away. I had a second intuition notebook that's sitting there in the lecture. It says, Notebook Lecture 05, Vectors and Rescaling. This one, I suggest you look at it yourself on your own. There's no programming to be done here, but I am going to give you, hopefully, as you run through this notebook cell by cell and read what's in there, you're going to get an interesting understanding of why you want to run standard scalar on your data before you do anything in machine learning. Okay? All right. Bye, everybody. Have a happy, happy weekend. On Monday, we'll do clustering.